Hello, I'm Mr. Muskeluk, your AP Chemistry teacher at Chem Advantage.
Let's do an AP Chemistry free response question. Here's the question. In a process of producing acetic acid, we're producing acetic acid. Oxygen gas, indeed, is bubbled into acetaldehyde. Here it is, CH3CHO. There's this containing a catalyst under pressure at 60 degrees Celsius. They give us the balanced reaction. In a laboratory test of this reaction, 20 grams of the acetaldehyde, this stuff, and 10 grams of oxygen were given. 2 reactants are put into a vessel. Now, quickly scanning over A, B, and C, they want to know the grams of acetic acid product. They want to know the excess reactant, because we have 2 of them. And they also want to know the percent yield. In AP questions now, free response questions, the booklet has a lot of spacing between the questions. In fact, these 3, A, B, and C, would be spaced out onto 2 pages. So you'd have plenty of room to answer the questions underneath each part of these. So don't worry about having a separate sheet anymore. This is something you should be able to answer within the FRQ booklet. But before we get going, you might have noticed that the formulas are a little bit unusual. You'd say, wait, CH3 and then the C again and HO? Why not just say C2H4O? Or why not have this consolidated? In fact, you might remember another formula for acetic acid is HC2H3O2. Well, to answer that, we need to look at the actual molecules. We'll be getting into organic chemistry later. And knowing a little bit about this is going to help you later on when we do Lewis dot structures. Because these substances, the aldehyde and organic acid, are very often used on questions to determine the structure of molecules. And this is the shape of the molecule. It's 2 carbons. One of them has 3 hydrogens around them, and the other has a carbon and a hydrogen and an oxygen. And this is why they use this formula. They're showing you, oh, look, a carbon with 3 hydrogens and a carbon with a hydrogen and an oxygen. And this also explains the acetic acid. The carbon here, the same single carbon group, and then our second carbon, instead of having an HO, this HO is called an aldehyde. You take an alcohol, which is an OH, and you oxidize it a little bit with a little bit of oxygen, and you get this new compound. This is how alcohols are metabolically processed. They're changed into an aldehyde, and then they're changed into a acid. This is how vinegar is made. And this is our acid group, a COOH. We've got a C with a double bond oxygen, and then an OH. So the formula actually makes sense because it gives you a hint of what the structure is like. In this case, when we have this formula, the acetic acid formula with the C2H3O2, you really can't figure out the 2 carbons here and the COOH alcohol. And with the aldehyde, again, you're not given a hint for this. So this type of formula gives you a hint as to what the molecule looks like, and that's why they use it in this problem. But we don't need to know that right now for this problem. In fact, actually, this problem could have had a situation later on where they'd ask you to do the Lewis structure of either the aldehyde or the alcohol. And if you knew their structure ahead of time, you'd be way ahead of the game. But let's go to this part, which is just about limiting reactants in grams. So A, B, and C ask about all sorts of masses, reactants, and products, and excess. So we're going to have to do quite a few calculations in terms of moles and grams. The best way to organize this is to use an ice chart. It puts everything in its place, allows you to check and see your answers. It's fast. It shows all the work that you need for the readers to grant you credit for your answers. Well, how are we going to do our ice chart? We'll start off, the very top of every ice chart is the formula. And here I've written the formula. You can see it's written out. I would have written it out on this page. Remember, you're going to have lots of room on an FRQ. So I've got my substances that I have to deal with. And I see that I've got 20 grams and 10 grams. Well, that's what we're going to start with. We're going to put that 20 grams, that mass, underneath the aldehyde. 20 grams, acetaldehyde, that's this. That's the reactant. Then 10 grams of oxygen Oxygen, okay, 10. Right there, 10 grams. This locates it for me. I'm not going to get these mixed up because I put them underneath the substances I'm dealing with. It's no longer written up here and vague. And they're put into a reaction vessel, so I'm going to have everything figured out in this reaction, and it's 0 grams of these. Of course, this is mass, and we're in chemistry, and the only way to figure this out is to find moles. And to find moles by now, please, I hope you know to automatically take a mass and divide it by its molar mass. So we need the molar masses of all of these. And the molar mass of this aldehyde, here we've got our calculator, and we know we've got 2 carbons. Okay, so 2 times, and by now you know 12.01. And then we'll add our hydrogens. Let's see, we've got 3 here, 1 here. So our 4 times our 1.008. We'll be using a hydrogen a lot, worth remembering. And finally, we get an oxygen that I'm sure you've remembered as being 16. These you should know by heart. And this gives us our molar mass of the aldehyde, our 44. And I'm going to put that right underneath my aldehyde. Everything in one place. All the aldehyde stuff is going to be in this column. That's why it's a table. Our oxygen, well, we can figure that molar mass out pretty quickly. One warning, though. Common mistake is for people to see oxygen and say, okay, oxygen is 16, and forget that it's diatomic. So don't use 16. Use that 32 grams per mole. And we're going to need the molar mass of the acetic acid because that's our product and they are going to ask us about it. So we'll have to take 2 carbons plus 4 hydrogens plus 2 oxygens. In fact, the only difference here is 16 plus our aldehyde. We've added 1 oxygen to it. There is our 60.5, but you could have, I guess, done the calculation too. Now note, it's very important to remember that you don't use coefficients in molar masses. This 2 and this 2 are ignored. We only use the formula, subscripts and the elements only. No coefficients for molar mass. That'll mess you up. This is what we're going to have to start with. We're going to come up with moles. 20 divided by, and this is the next row in our ice chart. This is our initial moles. You should know automatically grams to moles divided by molar mass. You shouldn't have to even think about that. That's automatic. So I'll take my calculator again, and I'll take that 20 grams and divide it by my answer, our 44.052. There's our moles of acetaldehyde. We have the amount, and we've got the moles, and we've got the I of our ice chart. Our 10 divided by 32. Oh, by the way, let's make sure this makes sense. Our calculator is seen here. We've got about 20. The molar mass is 44 for 1 mole. So we've got about a half a mole. Yes, and that's our answer, about a half a mole. And please don't write all these numbers down. That's embarrassing. 3 significant digits is enough. And we can take our 10 and divide that by 32 to find our moles of oxygen. And we don't have anything to divide here. It's going to be 0. Here's our next step. They've given us 2 reactants, and of course one of them is going to control this reaction, the limiting reactant. And the question, which one are we going to run out of first? A quick survey says, well, this is the lower number. I'm going to run out of oxygen first. No, you have to take into account the coefficients. You need 2 aldehydes for every 1 oxygen. So in terms of mass, it looks right, but here in terms of moles, look what's happening. We have 0.313, but we need twice as much of that in terms of aldehyde, and we don't have twice as much. We only have 0.454, so we're going to run out of aldehyde. Another way of getting this besides inspection is to take the mole amount, divide by the coefficients, 0.227. That's less than 0.313 divided by 1, so the smaller value really is the aldehyde when you divide by the coefficients. So a general rule, find the moles, divide by the coefficients. That smaller value will be your limiting reactant, what you run out of first. And I'm going to identify that. You're probably going to get a point just for identifying the limiting reactant. In fact, you might even get a point just for getting the right moles. Now, let me say that. My guess, you get 1 point for the moles, you get 1 point for identifying the limiting reactant. And I've identified it. Show your work. So we figured out what's controlling this reaction. And this is where we get to ice. I-C, here it is, C, the change. It's my favorite row because once you get part of the change row, one item, you can find everything based on the coefficients in the reaction. The change is dependent upon the limiting reactant because that's all that can react. We know all of this, 0.454, will be used up. I put it in boldface because this 0.54 will be used up completely. And once you have 1 molar amount, all the rest can be found based on coefficients. You didn't even have to know any of these other things here. You would just say, okay, 2 to 1. Therefore, this 0.454 divided by 2, 0.227, is going to be our amount of oxygen that's used. Notice I had a negative. And you could have very quickly gone here and say, oh, there's a 2 there, there's a 2 here, the same identical value. We're going to get 0.454 moles of our acetic acid. Change mole. I found 1. Therefore, if this has a 2 and this has a 2, then they both must have the same molar amount. If this has a 2 and this has a 1, in the change row, we have to have half as much of the 1, the oxygen. So there's our C. And you can see why it's my favorite, because you get one of them, and man, you get everything else. If there were 15 products or reactants, and you knew one of the mole amounts in the change row, you could find everything else out using these nice, beautiful, balanced equations. Now, we've got to now find out what our last part of the ice chart is. Well, the last part is end. What do we end up with? And notice I put a line there because it's just a matter of addition. And of course, subtraction, really, because our reactants are being used up. And our limiting reactant is all used up. That's why it's the limiting reactant. So we get 0 at the end. You don't have to worry about how many grams of the limiting reactant are left behind because there ain't any. Now we've got to do a subtraction here. And I'll do that in my calculator. I'll take my, I've got my 0.313. And I'll subtract. Don't erase your previous stuff. It can come in handy. The 0.227, or I could have taken the 0.454 divided by 2. Enter, and that's how much oxygen is left behind. 0.086, we have a little bit of oxygen left behind. Yeah, we see we've got about 0.313. We use up 0.227. A small amount of oxygen is left behind. And, of course, this last addition is going to be easy. And it's one of the answers that we'll want. It's the 0.454 of the acetic acid that's made. 2 aldehydes make 2 vinegars. That's what acetic acid is. In fact, that's how vinegar is made. They wanted grams. Okay, we know how to get grams. We've got our molar masses written here. And again, an ice chart like this, you've got your formula masses available for you, so you can use them easily. Set of multiplications are going to be pretty easy. Our final mass at the end, here you have our end moles, so our final mass that we have at the end of the reaction. I should have said end mass, but final mass sounds better. Of course, 0 grams. We'll take our 0.086 that we have in our calculator times 32. No need to type it out again. Use what's there. And that's how many grams of oxygen are left behind. 2.7 grams. Now, you can do the same thing here to get our acetic acid, but let's just do a little prediction ahead of time. We're starting off with 30 grams. Conservation of mass. When we're done, and we're at the end, we still should have 30 grams. We can have 2.7 grams of oxygen left. So to get 30, hey, my guess is going to be 27.3. Let's see if that happens. Let's see if my calculator does that correctly. I'm going to take my 0.454 and multiply it. And again, I wrote this down. You don't have to calculate it again. If you've got an ice table, you can find things quickly and do your calculations flawlessly. 60.05. Let's see if this makes sense. I've got the numbers in right. There it is. 27.3 grams. 2.7 plus 27.3, 30 grams. When we're done, we got 30 grams. When we started, we have 30 grams. So indeed, we know for A and B, everything's working out very, very nicely. This chart makes sense for us. We can be pretty certain that we've done things correctly. So let's see if we've answered everything. How many grams of acetic acid can be produced from these amounts of reactants? 27.3. Check. Make sure you've answered all the questions. How many grams of excess reactant would be remaining if the reaction is complete? Oxygen, 2.7 here on the ICE table. I'd circle it right underneath there. Even though readers, if you set up an ICE table, will understand everything and they will hunt the answers down for you. One of the common mistakes that readers very often say is students very often don't answer all the questions. Their first piece of advice is tell your students to check to see if they answered the questions. Answer the darn questions. And we've done that already for 2. On C, the reaction only produced 2.73 grams of acetic acid. What was the percent yield? Well, we haven't answered that yet, so we've got to figure that out. Percent yield, you've got that in your toolbox. You know, it's the amount that you made over what you could have made, the theoretical mass. Simple division, and we take the actual 2.73, yep. What we should have produced, 27.3, of course it's a percent, so times 100, and not too difficult to figure out that answer. 10%, not 100. A extra piece of advice here. Let's say you're running out of time, and you didn't have time to figure all this out. But you saw C here, 2.73 grams. What's the percent yield? It says, I know how to do percent yield really fast. It's what was made over what theoretically it should have produced. If you just wrote down final mass of acetic acid equals 30 grams, and then put 30 grams here, divided into 2.73, and got the correct percent, which would be for these values, you'd get that point. So don't give up on a problem if you don't have time to do all of it. Check and see, hey, is this an easy question? I can't do these 2, but I can do this. Make up a number and use it. So have we answered that question? Yes, there's our check mark. All 3, 1, 2, 3 for A, B, and C. There we go. An FRQ. The other parts of the FRQ would probably be coming up with the Lewis dot structures of the acetic acid. There's an FRQ, and now you know how to do an ICE chart and how to use it with a limiting reactant.